Imagine stepping outside, breathing in the air, and realizing that within that invisible expanse is the answer to one of humanity's really pressing challenges. What if the solution to global water scarcity wasn't hidden deep underground or, in distant oceans, but literally floating all around us, invisible but immense?
It sounds a bit like science fiction, doesn't it? But, well, this isn't. The
Mhm.
stark reality is global water scarcity is severe. I mean, UNICEF and the World Health Organization report that a staggering 1 in 3 people worldwide lack reliable access to safe drinking water.
1 in 3. That's huge.
It absolutely is. And this huge challenge sits right at the heart of the United Nations Sustainable Development Goal 6. That goal aims for universal water access and sustainable management by 2030. It's an enormous undertaking, really demanding some truly innovative solutions.
Yeah, it's easy to feel a bit overwhelmed by that number, by this sheer scale of the problem. But here's where it gets really compelling. The Earth's atmosphere holds over 13,000 cubic kilometers of water.
Exactly. 13,000 cubic kilometers. That's just a staggering amount, an untapped and sort of inherently decentralized freshwater source. He's just waiting for us to figure out how to actually access it efficiently.
So it's not just a theoretical concept, it's this massive, constantly replenished reservoir right above our heads.
Precisely. The fundamental challenge has always been how do we effectively and crucially sustainably capture it for human use?
And that, you, is our mission today. We're diving deep into this concept of atmospheric water harvesting, or AWH. We'll explore some groundbreaking new research that's moving this dream much, much closer to reality, focusing on sustainable and incredibly efficient new materials. Think about it, how scientists are literally transforming everyday biomass, yeah, things like wood pulp or even potato starch, into these revolutionary water-absorbing super sponges.
Hmm. Okay, so let's unpack the science here, pulling water straight from the air. We know devices that can do this have existed for a while, right? Decades even. What were some of the key limitations holding them back? Well, traditional AWH technologies, like those that basically cool air down to the dew point, kind of like an air conditioner does, or maybe those using basic desiccants like common salts, they've faced pretty significant hurdles. They're often either just too expensive to operate, incredibly energy intensive, or frankly, just not productive enough to be practical on a large scale.
Right, so cost, energy, efficiency, the usual suspects for new tech.
Exactly. Evelyn Wang, she's a mechanical engineer over at MIT, she actually described the current state of things as an explosion of efforts related to atmospheric water harvesting. It really highlights this intense focus now on finding a viable path forward.
An explosion of efforts. I like that. It captures the energy. And it suggests we're really looking for a breakthrough, maybe in the materials themselves. Which brings us nicely to hydrogels. These sound promising. What are they and why do they matter here?
Yeah, hydrogels are pretty cool. They're these soft, sort of porous networks, typically made of polymer fibers that can absorb just immense amounts of water. Essentially, they act like super thirsty sponges.
Okay, super sponges. Got it. But there's a catch.
Well, historically, yeah. The challenge with many of them has been sustainability. A big chunk of traditional polymeric hydrogels are made from petroleum-derived synthetic vinyl monomers. And that practice, contributes to plastic pollution. Projections even suggest these materials could account for maybe 20% of global fossil fuel consumption by 2050.
20%. Okay, so not exactly eco-friendly. We need the super sponge without the super pollution footprint.
Precisely. And that's exactly where this really transformative research from the University of Texas at Austin comes in. This is where the innovation really shines, I think. Giwa Yu, he's a chemist there, along with his team Wixin Guan, Yaxuan Zhao, Chuxin Lei, Yuyang Wang, and Kai Wu, they've developed something quite remarkable.
Okay, UT Austin, what did they figure out?
So their research, it was published in Advanced Materials back in February 2025. It proposes this universal strategy, a strategy to transform natural polysaccharides. Familiar stuff like cellulose from plants, starch like from potatoes, even chiasan from shrimp shells, into these highly effective and importantly sustainable hydrogel sorbents.
Wait, cellulose, starch, chitosan, stuff that's just everywhere. Why is using biomass like this so revolutionary for AWH?
Well, think about the scale. Natural polysaccharides make up over 90% of the world's carbohydrate mass. We're talking about an incredibly abundant, renewable, and widely available raw material source.
90%. Okay, so we're swimming in the potential ingredients.
Exactly. It represents a fundamental shift away from those petroleum-based materials towards bio-based ones. It aligns perfectly with global sustainability goals, creating more of a circular economy model.
It's incredible, taking everyday stuff like wood pulp or potato starch and tweaking it at the molecular level. So how do they actually do that? Their paper mentions a two-step molecular engineering process. Can you break that down for us? Keep it simple.
Absolutely. Think of it like giving these natural materials two new superpowers, basically. Step one is making them thermoresponsive. The team does this by grafting specific chemical groups, things called thermoresponsive groups, like hydroxypropyl or hydroxybutyl, onto the polysaccharide molecules.
Okay, thermoresponsive, meaning they respond to heat.
Precisely. And this is a game changer for energy efficiency. It allows the hydrogels to release the captured water really efficiently at relatively low temperatures, around 60 degrees Celsius.
Hmm.
Imagine a sponge you can just gently warm up to squeeze the water out instead of needing tons of force or really high heat. This cuts down the energy needed for desorption significantly.
All right, 60 Celsius. That's like just above typical hot tap water temperature. That does sound efficient. What's the second step?
Right. Step two tackles a common headache with some older salt-based sorbents. Salt leakage. You want salty drinking water. So they introduce what are called zwitterionic groups into the hydrogel structure.
Zwitterionic. Okay, new term for me. What do they do?
Yeah, it sounds complex, but the effect is neat. These groups create a unique salting effect. So unlike traditional materials where adding salt might actually hinder water absorption or just leak out, these groups make the material better at grabbing water, even when salts are present. And crucially, they stop the salt from leaching back into the collected water.
Whoa, wait. So the salt actually helps it grab water but doesn't leak out?
Exactly. You get the benefit of salts enhancing water uptake without the big downside of contaminating the water you collect.
Okay, that sounds like a genuine wow moment. No salt leakage, better water uptake. So how did these new materials actually perform in tests? What were the numbers?
The performance is pretty impressive, really showing the potential here. Their functionalized cellulose hydrogel, they call it ZHPC, which is short for zwitterionic hydroxypropyl. Cellulose showed excellent water uptake. Get this. It could absorb 0.86 grams of water per gram of hydrogel at just 15% relative humidity. That's a really dry environment.
15% RH. Okay, very dry.
Then, at 30% relative humidity, it jumped to 1.32 gram per gram. And at 60% RH, which is more moderate, it hit a remarkable 2.18 grams of water per gram of hydrogel.
2.18, so over twice its own weight in water at moderate humidity. That sounds really good.
It is really good. Achieving that level of uptake, especially under moderate conditions common in many dry regions, and then being able to release 95% of that water back out at just 60 degrees Celsius, that represents a huge leap forward in both how much water you can grab and how much energy you save compared to a lot of existing options. It means potentially more water for less energy in more places.
Those lab numbers are definitely impressive. But, the real acid test is always the real world, right? Outside the controlled lab environment. How did it do outdoors?
Right, that's the crucial next step.
Huh.
BYU's team did exactly that. They ran outdoor tests right there in Austin, Texas, over about a week in early March 2024. Using a prototype device, they managed to get a water production rate of up to 14.19 kilograms of water per kilogram of hydrogel per day using electrical heating.
14 kilos of water per kilo of gel per day. And was the water,
Yeah.
drinkable?
Absolutely. They did rigorous analysis on the collected water. It was very high quality, with metal ion concentrations significantly below World Health Organization standards, perfectly safe for consumption. This really signals a potential game changer for actual deployable off-grid water solutions.
And what's really compelling, you mentioned this isn't just about cellulose, right? They tested this on other biomass materials, too.
Yes, and that's key. It underscores the universality and versatility of their approach. They successfully validated this molecular functionalization strategy across cellulose, starch, and chitosan.
So it works on wood pulp, potato starch, shrimp shells.
Exactly. It means the potential pool of sustainable raw materials for these sorbents is incredibly broad. It's not just tied to one specific plant. It's a fundamental chemical engineering approach for these natural polymers. It really opens up questions for future work. If it works this well for these three, what other abundant natural resources could we adapt using this kind of clever molecular engineering?
Yeah, fascinating question. Now, the UT Austin breakthrough is clearly a massive step. But as Evelyn Wang said earlier, it's kind of one star in this rapidly expanding universe of AWH innovation. Let's touch briefly on what else is fueling this explosion of efforts, give folks a sense of the wider landscape.
For sure. There are definitely other exciting approaches bubbling up. For instance, back at MIT, Xuan Zhao and his team developed a different kind of hydrogel. Theirs uses solar energy directly to trigger the water release. It's a truly passive system.
Passive, so no electricity needed, just sunlight.
Right. And get this, it produced up to 1.2 liters per kilogram per day, even in the extremely dry air of Death Valley. That really highlights the potential for off-grid spots where sunlight is plentiful but power isn't.
Wow, Death Valley, if it works there. Okay, so passive solar, what else? Any other unique takes?
Well, Germicho's team over at the University of Nevada, Las Vegas, are working on a two-layer device. The idea is a layered architecture for higher efficiency. Their setup can apparently collect nearly 17 liters of water per day per kilogram of material in humid places, but still pull in a respectable 5.5 liters in arid conditions like Vegas itself. So that seems pretty adaptable.
17 liters in humid, 5.5 in dry. Okay. And then there are the MOFs, right? Metal Organic Frameworks. Omar Yagi at UC Berkeley, he's a big name there.
Oh, absolutely. MOFs are another really captivating class of materials. They're basically these porous atomic scaffolds, like microscopic scaffolding. They have these highly ordered nanometer-scale channels that can be precisely designed to attract and trap specific molecules, in this case, water vapor.
So like custom-built molecular cages for water.
Kind of, yeah. Now, they might hold a bit less water by weight compared to some of these hydrogels we've discussed, but their big advantage often lies in speed. They can capture and release water incredibly quickly, allowing for many, many cycles in a short amount of time. Yagi has reported some preliminary unpublished tests where prototype devices using a tweaked version of his team's MOF might produce an incredible 200 liters of water per kilogram per day.
Whoa, hold on. 200 liters per kilogram per day? That's astounding.
It is an astounding number, yeah. And often they can do this using just small amounts of added heat, potentially even waste heat from other processes. It hints at massive scalability.
And isn't his technology already moving towards commercial use?
It is. Yagi has licensed the tech to a California startup called Atoko. They're exploring some really innovative uses, like generating water to help cool huge data centers. They'd effectively harness the waste heat from those centers to speed up the water cycling. They're even planning pilot-scale facilities in Texas and Arizona soon. It shows the immediate potential beyond just, drinking water.
Data centers. That's clever. Tapping waste heat. And speaking of real-world stuff and pioneers, there's Cody Friesen at Arizona State University, his company, Source Global. They're already putting panels out there, right?
Yes, Source Global has already installed their water-producing hydro panels at over 450 sites around the world, mostly in remote off-grid locations, providing clean water right where it's desperately needed. He's a real AWH pioneer.
So we have these advanced materials like hydrogels and MRFs being developed and companies already deploying current tech. What does this all mean for the future of water access globally?
Well, Friesen is incredibly optimistic about it. He believes that as manufacturing scales up, just like we saw with solar panels and batteries, the costs are going to drop significantly. He actually predicts that atmospheric water harvesting will eventually become the lowest cost potable water on the planet.
The lowest cost potable water. That would fundamentally shift our whole relationship with water as a resource.
It absolutely would. It's a powerful vision, and it really ties together everything we've talked about today, doesn't it? From the deep science of molecular engineering to the potential for massive global impact.
Yeah, it really does. It shows the immense potential when innovative material science tackles a critical global need head-on. It's about rethinking what's even possible.
Not just for water, but for how we approach resource management in general, I think.
Okay, so let's try and boil this down. What are the key takeaways for you from this deep dive into atmospheric water harvesting?
All right, first key insight for me. AWH isn't just about collecting water drops. It's a profound shift towards decentralized renewable water access. We're literally tapping into this vast, omnipresent global reservoir. It fundamentally redefines what we mean by scarce resource.
Right, decentralized and renewable. Okay, second takeaway.
Second, the breakthrough. Scientists like Yu and his team at UT Austin have essentially cracked the code. They're transforming ubiquitous, everyday biomass, things like potato starch or wood pulp, into these hyper-efficient super sponges. This isn't just one new material. It feels like a blueprint for globally scalable, truly sustainable water production, potentially even repurposing agricultural waste streams.
Sustainable and scalable using waste. Love that. And finally,
this whole innovative approach promises clean, accessible water for communities everywhere, especially those off-grid or in emergency situations. It's not just about providing water, though. It's about pushing forward global sustainability goals, specifically UN SDG 6 for clean water and sanitation, and maybe even 12 for responsible consumption and production. It helps build a more resilient future.
Yeah, this deep dive really hammers home how ingenious material science, often inspired by nature, using nature itself, can turn these seemingly intractable global challenges into, well, solvable problems. It offers some incredible hope for a water-secure future for everyone.
It really underscores that sometimes the most elegant engineering solutions are found right there in the biological world around us. We just need to learn how to adapt to them.
Absolutely. So here's something to think about as we wrap up. If we can truly pull abundant, clean water directly from the air using materials derived from, say, agricultural waste, what other impossible challenges might we overcome by looking more closely at nature and applying some ingenious molecular engineering?